Hey, Wheaton North, Mr. Igler here. We're going to go through a little bit of gas stoichiometry and talk about how to calculate gas density, just a couple of example problems to work on. Now, by combining gas laws and the ideal gas law with stoichiometry, the problems get kind of large and kind of hard to manage, so it's really important to plan your work. You're always going to be given a gas, and with that gas, you're always going to have to have at least some of the pressure, temperature, volume variables to work with. Now, I leave out moles there because moles is always going to be used in stoichiometry, right? So a lot of times we're going from the ideal gas law to calculate moles, and then from moles we can go into the stoichiometry, and from the stoichiometry we can even go to another gas if there's another gas in the reaction equation, and you could be calculating a pressure, temperature, or volume of that second gas, of like a product. So think of this as like reactant gases potentially, and this as product gases. You could start in the middle too. It could be the case that you are just given a stoichiometry problem and then asked to calculate what a gas variable would be, after the reaction. Let's look at adding an example here. We're going to calculate the volume of CO2 at STP produced from the decomposition of 152 grams of calcium carbonate, and then it gives you a reaction here. Take a step back from the problem and think about where we are in this process and where are we going. It's the only number it gives us. It gives us STP, which is a pressure and temperature, so that's going to be important, but it also just gives us the mass of a reactant, right? And the reactant is a solid, so we're not going to be using any ideal gas laws because we're given an amount of a solid. So let's start with the stoichiometry, and then from there we can get to the pressure, temperature, volume of the gas, okay? So we're given this 152 grams. From grams we can go to moles. The molar mass is pretty much exactly 100, so it's just 1.52 moles of calcium carbonate. And look at the mole ratio in our balanced equation. It's a 1-to-1, and so 1 mole of calcium carbonate would be 1 mole of carbon dioxide. Now that we have a moles of a gas, now we can use the ideal gas law to figure out whatever it is we're trying to figure out. In this case, it's volume. This happens to be at STP, and so you can use the 22.4 conversion, and it comes out to 34 liters of carbon dioxide. Next example. Methane has this volume, temperature, and pressure. It's mixed with oxygen at this volume, temperature, and pressure. The mixture is then ignited to form carbon dioxide and water. So here's your chemical reaction that's taking place, right? So we're actually given two gases before the reaction takes place. And then we're trying to figure out the volume of carbon dioxide at this given pressure and this given temperature. So this one's a little more complex. Again, take a step back from it. It helps to have a chemical equation to work off of. We're given temperatures and pressures and volumes of each of these individual gases, and then asked to figure out how much of this product is going to be made. So we're going to have to start with the ideal gas law, but in this case we have to do both of these because we have two reactants, right? It's kind of like a limiting reactant problem. It helps a lot you could color code, you could like underline with different pens, but what I like to do that's really helpful is to write all the numbers. Because we're given so many numbers in the problem, it's really helpful to just take a few seconds and write down all the numbers for each of the species in the reaction. So here's all my methane numbers, here's all my oxygen numbers, and then I have 2 carbon dioxide numbers. Now, like I said before, moles is going to involve the stoichiometry, so we can't do any stoic, we can't go from reactants to products until we get to moles. So let's figure out moles of both of these gases. Rearranging the gas law, N equals PV over RT, run those numbers for each of them. 1.89 moles of methane and 1.75 moles of oxygen. Now, here we have two amounts of two different reactants. That doesn't mean that we're going to make all of it, right? We're not going to use all of this. If we have 1 mole of methane, that requires twice as much oxygen. So if this was 0.2, then that would require 0.4 moles of oxygen, which we have way more than enough. So we're not going to run out of oxygen, we're going to run out of methane far before we run out of oxygen. And so this is our limiting reactant, and because the ratio is 1-to-1 here, if we use up all of our methane, we're going to produce the same number of moles of carbon dioxide. Now that we have moles of carbon dioxide, now we can go into our ideal gas law. We're trying to solve for volume, and so I rearranged the formula for volume, plug in those numbers, and you end up with 2.47 liters. All right, here's a gas density example. Remember the formulas that we went through in class. Molar mass is density times R times T over P. We could use that one if you can remember it. If that comes to your head, then certainly use that one. There's actually another way you can manipulate the ideal gas law in order to figure this out. So pause the video, rearrange any formulas that you can think of, like the ideal gas law, and you should be able to figure out the molar mass of this gas. So this is one way to figure it out. Molar mass is dirt over P, essentially, where you're just plugging in your density of your gas that's given, R value, temperature, over your pressure, and you get 32 grams per mole. Now, if you don't remember this, if you can't think of this, if this was on a test or something, you can still solve it just with the ideal gas law. One thing that you have to remember is that the number of moles is equal to mass over molar mass. Subbing that in, we end up with this, right? Pressure volume equals mass over molar mass times R times T. Now, density is not really in here. It's not written in here clearly, but density is mass over volume. If we have a density of 1.95 grams per liter, then if we had 1 liter, we would have 1.95 grams, right? So we can treat volume as 1 and our mass as 1.95. When we plug those numbers in, solve for mm, notice it's 1 over molar mass, and so you'd have to do the reciprocal to solve for molar mass. But you end up with the same number, 32 grams per mole. So this is most likely oxygen gas, right, O2. One last thing that I want to mention, and this is an important point because you will see this a couple times in chemical reactions. The volume of gas is proportional to numbers of moles, right? Same thing with pressure. Pressure is proportional to number of moles. So if you're given a reaction that has gases on both sides of the equation, like this one, the volume and the pressure, for that matter, is dependent on whether you have more products or more reactants. So if you have a container with this reaction and it's largely reactants or it's largely products, which one of those situations would have a greater volume? You would have a greater volume if you have more reactants, right? Because on this side of the reaction, there's essentially 3 moles of gas, right? There's 2 molecules of hydrogen and 1 molecule of oxygen. So you could think of that as 2 moles and 1 mole, a total of 3 moles of gas overall when we have just the reactants. But if we form all the products, the volume would actually decrease because we have fewer particles of gas. We've basically taken those 3 molecules and we've combined them into a total of 2 molecules. So our pressure would go down and or our volume would go down. This is important to keep in mind, and this will be important when we talk about equilibrium as well, because you can shift the equilibrium by exerting pressure on the system depending on which side of the reaction has more or less gas. So if you go back to that calcium carbonate example earlier in this video, there is no pressure initially, no gas pressure from carbon dioxide initially because it's all solid. Once you go to products, now all of a sudden there's gas pressure being added because we're producing a gas. If you have any questions on this, make sure you write those down now and bring them up in class. This is Mr. Yerler signing off.